All right, section 9.2, polar graphs and equations. Get our calculators out and ready because we're going to be graphing a whole bunch of stuff. I would also probably, it's important to know the different polar equations and graphs and the equations that go with the graph. So I want you to make sure we remember those little pieces. So maybe make a note card or a Quizlet that has the equation, the name, and then what the graph looks like with it. So if we're on a rectangular grid, we have coordinates A and B, and they correspond, A corresponds to 1, 2, B corresponds to -3, 1. And we compare that to a polar grid, which is a series of concentric circles. And each circle represents a unit. So we find the angle, the theta that we are from our coordinate, and then we go out that many units on our circle. So an equation whose variables are polar coordinates is called the polar equation. The graph of a polar equation consists of all points whose polar coordinates satisfy the equation. So just like we have equations of circles, equations of different things in rectangular, we will now have different equations in polar, and being able to see, identify and graph polar equations by converting to rectangular equations. So if we have the polar equation r equals 3, so if r equals 3, we're going to convert it to a rectangular equation. So we're going to go ahead and square both sides, because everything we know about r is related to x squared and y squared. So we're going to rewrite it as r squared equals 9. We're going to substitute r squared for x squared plus y squared. So instead of this r here, we have x squared plus y squared. So we're just using this identity. And we can see that r equals 3 is a circle. The center is at the pole, and it has a radius of 3. All right, so the next one we're going to look at is when we have just theta. The first one was we had just r. This one is just theta. So identify and graph the equation theta equals pi over 4. So we're going to remember when we are solving for angles, we want to, in this situation, we want to push to tangent. So we're going to take the tangent of both sides. So tangent of theta equals the tangent of pi over 4. We know tangent is equal to y over x. The reason we pick tangent is because he only has y and x, and we can convert to rectangular in one step. So, and then the tangent of pi over 4 is 1, so we know y over x equals 1. We want to solve that for y because normally in rectangular coordinates we have our equation solved for y. We get the line y equals x. When we graph that, we see that we go out we rotate pi over 4, and it's a line. Check this out, it not only goes pi over 4, but it goes in the direction 180 from pi over 4, which is 5 pi over 4. It's this entire line. Because we can also substitute in anything for r. So if I had a negative r, if r is -5, we're still getting pi over 4, but that changes the direction for us. So the previous two were simple, simple, simple. They were only, when we only have r or only have theta. And so now we're going to start throwing in some other stuff. So if we have r sine theta equals 2, we know that y equals r sine theta. So we're going to rewrite the equation as y equals 2. So we get a nice horizontal line. And it may seem a little bit odd, because if you look at it in relationship to polar coordinates, we're going here to the top of our circle that is 2 units in radius and creating a horizontal line. So it really, y equals 2 is a rectangular graph, but we have to apply it onto a circular polar graph. All right, r cosine theta equals -3. This will give us a vertical line because we replace r cosine theta with x. By the way, this is baby stepping us into more complex substitution and solving in polar coordinate operations. So we get x equals -3. That's a vertical line. The circle that has a radius of 3, but to the left of the polar axis, that's this line here. All right, so here's our theorems. Here's our meat and potatoes. Let a be a non-zero number, then the graph of the equation r sine theta equals a is a horizontal line, a units above the pole if a is greater than 0, and a absolute value a units below the pole if a is less than 0. The graph of the equation r cosine theta equals a is a vertical line, so a units to the right of the pole if a is positive, and absolute value of a units to the left of the pole if a is negative. So we have graphed a circle, a slanted straight line, a horizontal line, and a vertical line. So that's 4 different graphs we have polar, and it's important for us to know the equations that go with those. So we're going to graph r equals 4 sine theta. We are going to multiply both sides by r. This is a skill you're going to have to know how to do inherently. So if you get to a place like this and you're going, I have no idea what to do, squaring both sides will give us a sine squared, and that doesn't help us in this process at all. But multiplying both sides by r is important. So in some way, you got to highlight, star, emphasize this step because it happened yesterday in our notes and it's happening again today. So multiplying both sides by r is a real option, viable option. So we get r squared equals 4r sine theta. We know r squared is equal to x squared plus y squared, and that y equals r sine theta. So we're going to use both of these properties to convert this back to rectangular. So I'm going to replace r squared with x squared plus y squared. And I'm going to replace r sine theta with y. If I move 4y to the left-hand side and complete the square, and rewrite this as a squared term, I can see that this is a circle whose center is at 0, 2 with a radius of 2. So r equals 4 sine theta is a circle centered at 0, 2, so over 0 up 2. The radius is 2 because this is r squared is 4, so the radius is the square root of that. It goes up 2 and down 2, and it sits right here. So let's look at that process with cosine. So we got r equals -2 cosine theta. What do you think our first step is going to be? Multiply both sides by r. And we do, and we get r squared equals -2r cosine theta. We substitute the r squared for x squared plus y squared. Substitute the r cosine theta for x. Move the -2x over. Complete the square. Write it as a squared term. And now I can see that this is a circle whose center is -1, 0, and who has a radius of 1. So it looks like this, -1, 0, radius of 1. When we have, so we're going to take a look just real quick at r equals sine theta. So on your graphing calculator, you can set your calculator in terms of polar coordinates. So go ahead and go to mode. We want it definitely in radians, and it's the fourth line down. It says function parametric polar. So we're going to go to the third one, POL, and make sure our mode is in polar. So that way when we go to graph, you hit y equals, instead it says r1 equals. So this is how you graph polar on your calculator. So when we graph sine theta, we get this guy here. When we graph r equals 2 sine theta, we get this guy right here. When we graph r equals 3 sine theta, we get this guy here. Do we see the pattern? Which is? What's your coefficient on R1? 1. What's your diameter for that circle?
Our diameter is 1.
Diameter is 1. For R2, the coefficient is 2, your diameter is 2. So, and 3, your coefficient is 3 and your diameter is 3. Sine theta is y. So because you are related to y and the sine, your circles open up on the y-axis. That's how I remember it. Sine is y, we open on the y. If we were to do negative sine, -2 sine and -3 sine, it would open on the y-axis just below the x-axis. So if we look at cosine theta, because cosine is related to x, it opens along the x-axis. The diameter is the same as the coefficient. And when we go negative, it'll go along the x-axis in the negative direction. All right, so here's properties. If we have r equals 2a sine theta, the reason we go 2a is because that coefficient represents the diameter. Most of what we want to talk about is related to radius. So the relationship between diameter and radius is factor of 2. That's where this 2 comes from. So if I have r equals 2a sine theta, that is a circle, the radius is a, the center is at 0, a, and it is in rectangular coordinates. Same with the negative. If I have a negative in front, the center is now at 0, a, and the radius is a. Cosine. If I have cosine, then the a value is the x-coordinate for my center. All right, now we're going to talk symmetry. If you have symmetry with respect to the polar axis, which means you're reflected across this line here, from 0 all the way out to infinity. If you replace theta with the negative theta and get an equivalent equation, then you have symmetry with respect to the polar axis. And so we may have to go back into our identities, like cosine. So cosine, when you plug in negative theta, it's the same as cosine of theta. And then same thing with secant. Symmetry with respect to the line theta equals pi over 2. Theta equals pi over 2 is this line right here. When I have symmetry, it's as if we are mirrored over that line. It starts here at 0 and goes up to infinity. So if we replace theta with pi minus theta, and we get an equivalent equation, then the graph is symmetric with respect to theta equals pi over 2. Respect to the pole or the origin. So if I have symmetry with respect to the origin, I replace r with negative r. And if I get an equivalent equation, then I have symmetry with respect to the pole. Okay, the reason we do symmetry is so we can graph polar equations by plotting points. Because if I know I have symmetry, I can plot the points. Okay. The first equation we're going to graph is called a cardioid. What is our root word in cardioid? What is it? What does card usually represent? Yeah. If I have cardiac arrest, what happens to me? My heart stops. So cardioid is kind of a heart shape. So r equals 1 minus sine theta. We're first going to test for symmetry. So we replace theta with negative theta. And we get 1 minus sine negative theta. We know sine of negative theta is equal to negative sine theta. So we go 1, it changes it to 1 plus sine theta, not an equivalent statement. So it's not symmetric with respect to the polar axis. We're going to see if it's equal to, if it's symmetric with respect to the line theta equals pi over 2. So we're going to replace theta with pi minus theta. We're going to use the identity to rewrite sine of pi minus theta, and we get 1 minus sine pi cosine theta minus cosine pi sine theta. We know that the sine of theta is equal to 0, and we know that the cosine theta is equal, sine pi equals 0. Cosine of pi is equal to negative 1. So we get 1 minus, this goes away. Negative and negative give you a positive, but then I have another negative here to give you minus sine theta. So I do get the same statement. So the graph is symmetric with respect to the line. Theta equals pi over 2. All right, so we did all that. Now we're going to test if it has symmetry with respect to the pole. So we're going to replace r with negative r. So it's negative r equals 1 minus sine theta. So if I divide everything by -1, I get r equals -1 plus sine theta. That test fails. So we are going to, we already did that. So it's not symmetric with respect to the whole. So the pull test failed. So we're only symmetric with respect to the line y equals theta equals pi over 2. So what we're going to do is we're going to find some values so we can graph this puppy. So when we plug in pi over 2, sorry, negative pi over 2, we get 1 minus -1, which is 2. When we plug in negative pi over 3, we get 1 minus -√3 over 2, which is about 1.87. When we plug in negative pi over 6, we get 3/2. We plug in 0, we get 1. Pi over 6, we get 1/2. Pi over 3, we get 0.13. And pi over 2, we get 0. When we plot these points, so here we are at negative pi over 2, 2, negative 3 pi over 2, sorry, negative pi over 3, 1.87. So you go out. Now these are increments of 0.5s. So you go out to 1.87. At negative pi over 6, we're at 3/2. At 0, we're at 1. At pi over 6, we're at 1/2. And at pi over 3, we're at 0.3. And then at pi over 2, we're back down to 0. We have symmetry with respect to the line theta equals pi over 2. So we can just draw the second half on the left-hand side here. And this is kind of a heart-shaped. That's why it's called a cardioid. Okay, so if we graphed 1 plus sine theta, we get this guy right here. If we graphed 1 minus cosine theta, we get this little guy here. If we graph 1 plus cosine theta, we get this little guy here. Can we identify a pattern? All right, so when we graph this guy right here, we see the difference between the top and the bottom is 2. So from here to here is 2 units. If we change this to a 2 plus sine theta, the difference between the top and the bottom of the cardioid would be 4. Sine opens up along the y-axis. Cosine opens up along the x-axis. If I have a minus cosine, I open up to the left. If I have a plus cosine, I open to the right. I think these look more like apples than hearts, personally. All right. So cardioids are characterized by the equations r equals a times 1 plus cosine theta, or 1 minus cosine theta, or 1 plus sine theta, or 1 minus sine theta, times all times by a. Where a is greater than 0, the graph of the cardioid passes through the pole. All right, let's take a look at the limacon. He is the French brother to the cardioid. This is a limacon without an inner loop. we're going to graph the equation r equals 3 plus 2 cosine theta. Let's test our symmetries. We're going to replace theta with negative theta because we have cosine. We know that cosine is an even function, so he pops back out 3 plus 2 cosine theta when we put in negative theta. So he is symmetric to the polar axis. Testing symmetry with respect to pi over 2. We say theta is now pi minus theta. We use the angle subtraction identity to rewrite that as cosine pi cosine theta plus sine pi sine theta. Cosine of theta, cosine of pi is -1. Sine of pi is 0. So this knocks this guy out, and this makes the cosine of theta equal to -2 cosine theta. Not the same as our original function. So it is not symmetric with respect to pi over 2. If we replace r with -r, we do not get the same. So that test fails as well. We replace theta with theta plus pi. That test fails, so the graph may or may not be symmetric with respect to the pole. So let's take a look by plotting some points. So when I plug in these different values for theta, I get out. So when theta is equal to 0, I get out 5. When theta is equal to pi over 6, I get out 4.73. Then 4. Then 3. Then 2. Then 1.27. Then 1. And we know it's symmetric with respect to the with respect to the polar axis. So we can just copy those same values mirrored across the polar axis here. And that's a limacon. This is a limacon without an outer loop. Some limacons have a little loop that's right here. So if we take a look at 3 different graphs, the first graph is r equals 3 minus 2 cosine theta. Then r equals 3 plus 2 sine theta. Then r equals 3 minus 2 sine theta. So if we look, this one opens along the negative side of x, it opens to the left. The distance from the origin to your limacon is 3 on each side. I think it's 3. 1, 2, 3. And for 2 sine, it opens up. For -2 sine, it opens down. So hopefully you see those patterns. Okay, so limacons without an inner loop have the following equations. So it's either a plus b cos theta or a minus b cos theta. Or the sine versions of those are a plus b sine theta or a minus b sine theta. Where a and b are greater than 0, a is greater than b, and it won't pass through the pole. Inner loop on with our limacon. So we get r equals 1 plus 2 cosine theta. So let's test for symmetry. Polar axis symmetry, we're going to replace theta with negative theta. I have cosine, so it's going to be symmetrical with respect to the polar axis. So what I have on the top, I'm going to have on the bottom. Testing for theta equals pi over 2 symmetry, and it's going to end up negating the cosine term. Bless you. So it is not symmetric with respect to pi over 2. If I replace r with negative r, does not give me the same thing, so it may or may not be symmetric with respect to the pole, so we replace theta with theta plus pi. The test failed, so the graph may or may not be symmetric with respect to the pole. This darn pole test is killing us. Okay, so let's plot some data values. You can actually pull this up on your graphing calculator if you want to go ahead and put the equation in. So 1 plus 2 cosine theta. And then if you go to your table, we want to start our table at 0. We'll increase by pi over, let's go pi over 12. That way we can get all of them. Okay, so then I get 0, 3. Pi over 6 is about 2.73. Pi over 3 is 2. Pi over 2 is 1. 2 pi over 3 is 0. 5 pi over 6 is negative 0.73. And pi is negative 1. So if you follow those, it comes all the way around here, loops in, and stops here. We have symmetry with respect to the polar axis, so we're going to go ahead and put the second part of that onto our graph. Limousin with an inner loop. So here is 1 minus 2 cosine theta. Here is 1 plus 2 sine theta. Here is 1 minus 2 sine theta. Do we notice anything do we notice a pattern? Thankfully, the same pattern follows. If we're cosine, we open across the x. If we're sine, we open across the y. And if I'm negative, it's to the left. If I'm cosine, if I'm negative, it's down if I'm sine. And then take a look at the width of your inner loop. For each one, the diameter of the inner loop is 1. And then the remaining amount here is 2. All right. So limousin with an inner loop are similar to limousin without an inner loop, except that A is less than B. So our values out front are less than our coefficients to our trigonometry. Okay, so we're going to graph now of rows. R equals 2 cosine of 2 theta. So if we check for polar axis symmetry, we get a yes, because cosine theta is equal to cosine of negative theta, our identity. Who we are also going to get if we replace theta by pi minus theta, we get 2 cosine of, because I got the 2 on the inside, 2 pi minus 2 theta, which if I add 2 pi to anything, it's going to get me around to the same theta I was at before. And we know cosine, when I have negative 2 theta, is the same as cosine of 2 theta. So this test, it's symmetric with respect to the line theta equals pi over 2. So I got a yes in the polar axis, a yes to the theta equals pi over 2. Yay! And since the graph is symmetric with respect to both polar and the line theta equals pi over 2, it must be symmetric with respect to the pole. So when you get a yes here and a yes here, you will get a yes on the third. So if we plot some points, we see that if theta 0, we're at 2. If pi over 6, we're at 1. Pi over 4, we're at 0. Pi over 3, we're at negative 1. Pi over 2, we're at negative 2. It makes this nice little rounded shape here. We have symmetry with respect to the axis, so this little half will have a matching half here. And then its little buddy, so because it has symmetry with respect to the line theta equals pi over 2, we can duplicate that over here. And it'll have a petal over here too. Because we have symmetry with respect to theta equals pi over 2, this half of the petal will also be duplicated here. And because we have symmetry with respect to the line, to the polar axis, this petal is duplicated up here too. So if I have a rose, I get 4 petals out of here that are that have symmetry. Polar axis and it equals pi over 2. All right, so now we're going to see about how many petals each, what I have to change here to get different petals. So if I go 2 cosine 4 theta, 1, 2, 3, 4, 5, 6, 7, 8 petals. 2 cosine 6 theta, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many petals do we think our cosine of 3 theta is going to give us? So if 4 theta gave us 8, 6 theta gave us 12, 3 theta should give us 6. Five theta should give us 10. 7 theta should give us 14. But that's not the pattern. That's why we're talking about it. Okay, so if I have an even number as a theta coefficient, I will get double the amount of petals. If I have an odd number as my theta coefficient, I will get that amount of petals. That's the pattern. So roses are described by r equals a cosine n theta and r equals a sine n theta. They have graphs that are rose-shaped. If n is even, the rose has 2 n petals. If n is odd, the rose has n petals. Lemniscates. I know, it just keeps going on and on. So a lemniscate, it has the form of r squared equals trig function. you guys, we're just going to leave it to you to verify the graph is symmetric with respect to the pole, because of the symmetry with respect to the pole, we only need to consider the values of theta between 0 and pi. There are no points on the graph between pi over 2 and pi, since r squared less than, since you can't have r squared less than 0. Okay, so let's take a look at when we plot these points. So r squared is equal to 4 sine 2 theta. We get this petal shaped right here if we go from 0 to pi over 2. We're symmetric with respect to the pole, so we get its mirror across the line theta equals pi over 4. This is like a little infinity. Super fun. So the equation of a lemniscate is r squared equals a squared sine 2 theta, or r squared equals a squared cosine of 2 theta. And these have propeller shapes. Okay, so when we have a spiral, r equals anything with just theta. So in this case, we have e to the theta over 5. It doesn't have any symmetry, but let's look at the graph. So what happens is at negative 3 pi over 2, we're at 0.39. So it kind of starts down here. At negative pi, we're at 0.53. At negative pi over 2, we're at 0.73. Oh, they didn't record that. At negative pi over 4, oh, it's down here. We're at 0.85. At 0, we're at 1. Pi over 4, we're at 1.17, 1.37, 1.87, 2.57, and we just keep, as we spiral outward, which is what's called a spiral, we just keep getting larger and larger. This one's called a logarithmic spiral, since its equation can be written as theta equals 5 natural log of r, and it spirals infinitely both toward the pole and away from it, so it gets closer and closer, closer to the pole. Okay, so let's look at the summary of all that we have discussed. No need to write this down. We are just recapping. So we've got our lines. We can make a line here. We can make a vertical line. We can make a horizontal line. We've got our circles. We can move their, if they open on the x-axis, their cosine. If they open on the y, their sine. We've got our cardioids. They kind of look like little hearts. We've got our limacol without an outer loop. And then we have a limacol with an inner loop. We have a lemniscate. Looks like a propeller. A rose with 3 petals or odd number of petals. A rose with 4 petals. And to graph the equation quickly, we recognize this as a cardioid. The period of sine is 2 pi, so form a table using 0 to 2 pi. Compute r, plot the points r theta, and sketch the graph of the cardioid. Cardio, because really you get pumped up, guys. Okay, so it'll look like this. identify what shape it is, and then make a table. And that's it.